All right, good morning, you guys. I'm taking all the problems that I had for Quiz 9 Partner Challenge, and I'm just making this into another review lecture for you guys to have. Okay, so find the percent nearest hundredth of a standard normal model in the region. Okay, so here I'm saying z is less than negative 1.02, right? If I visualize that, which you know I love, here would be my mean. Here would be about z at negative 1.02. And I want it to be less than. So I'm looking at that lower tail right there. So I know that when I'm using z-scores, my placeholder for negative infinity can be negative 99, right? We're using just a placeholder for infinity. So when I type this into my calculator, I can say normal CDF from negative 99 to negative, let's see, 1.02 with a mean of 0, standard deviation of 1. So normal CDF, negative 99 to negative 1.02, mean of 0, standard deviation of 1. So that's going to get me a percent, let's see, decimal, I'm going to get about 0.1539. So as a percent, I would write that as 15.39%. Okay, for 2, find the z-score to the nearest hundredth that corresponds to the top 15%. So remember that the top 15% is really the same as the bottom 85. So if I visualize that, here's my normal curve. Here's the top 15% roughly. And then here would be its complement, the bottom 85. And I'm trying to solve for that z-score right there. So I can use inverse norm. Proportion below, area below is 0.85 with a mean of 0 and a standard deviation of 1. So if I type that in, inverse norm, 0.85, comma 0, comma 1. So that's going to get me a z-score of about 1.0364. So there's 4 decimal spots. The instructions do say nearest hundredth, so I will record it as 1.04. Find the percent to the nearest hundredth of a standard normal model in this region. So once I see my absolute value bars, I know, oh, that reads as a magnitude. Right? It's really asking me the distance from the mean. So it's saying that the distance from the mean, where the z-score is 0, right, it's going to be more than 1.23 standard deviations away. So if I visualize that, here's my normal curve, here's my mean right smack in the middle. So here I'm about 1.23 z-scores above and here below. And a z-score, again, it's just saying this is how many standard deviations you are away from the mean. So here we're saying that it's more than 1.23 away from the mean. So I'm looking at my 2 tail regions. Okay, we should note that their areas are going to be exactly the same because they have the same magnitudes, right? They have the same distance away from the mean. So over here, negative infinity, my placeholder will be negative 99. Positive infinity, placeholder will be positive 99. I can find just one of those and then I can double it to get to both of the regions. So I'm going to do normal CDF from negative 99 to negative 1.23, mean is 0, standard deviation is 1. Okay, once I get this, I'm just going to double it. So normal CDF, negative 99 up to negative 1.23, mean of 0, standard deviation of 1. So enter, I get 0.1093. So I know the area here is 0.1093. The area here is the same. So I have to double it, which is going to get me 0.2186, and as a percent, 21.86%. Okay, find the z-scores, again, nearest hundredth, that correspond to the middle 60%. So middle 60%, let's make a picture. So here's my middle 60% roughly, which leaves me with 40% that I have to split two ways. So 20% here and 20% here. And I'm looking for those two markers, here and here. And I know again that they're going to be opposites because they have the same magnitude, same distance from the mean. So here I need to look at that proportion below as an area of 0.2. And then I can do inverse norm, 0.201, just like that. So let me slide it to here so you can see both. So inverse norm, 0.2, 0, 1. And that's going to pump out the z-score of about negative 0.8416. So that would be the z-score here. Here would be its positive counterpart. And if I'm going nearest hundredth, I would say that z is about negative 0.84 and positive 0.84. Okay. All right, next up in 5. In the diagram, the shaded region represents approximately 99.7% of the scores on a standardized test. Estimate the mean and standard deviation. So 99.7% of the scores, that tells me then that these are 3 standard deviation markers, that this is 3 standard deviations above and this is 3 below the mean. So if I follow my general rule, 68% of my data should fall within plus or minus 1 standard deviation of the mean. 95% should fall within plus or minus 2 standard deviations of the mean. And 99.7% should fall within plus or minus 3 standard deviations of the mean. So that tells me then that these are 6 standard deviations apart. Right here is the mean. I could show these little notches to show how it's splitting up just like that. Here is the 3 above, here is the 3 below. Mean is easy. If this is where my mean should fall, right smack in the middle, mean is just an average of those two numbers. So for my mean, I really just have to take the 42, add the 120, and split it 2 ways. So here I'm taking 162, dividing it by 2, and I would get 81. So my mean is 81. Okay, with the standard deviation, well, standard deviation, I need to know, well, what's the distance between them? So if I take 120 minus 42, that keeps me with positive numbers, but I could go opposite and just take absolute value. Doesn't matter. So 120 minus 42, and then I have to split it 6 ways. So if I take 120 and I subtract 42, I'm going to get 78. Split that 6 ways, and I get 13. So standard deviation is 13. All right, next, a finding missing parameter question. So here we're told the mean. We're told that 76% of our data is above 38. So 38 right there, that is our observation. We want the standard deviation. So, you know I love a picture. Let's draw one out. So here we know that's our mean. Our mean is 40.35. So 76% of the data falls above 38. So let's put a 38 about here. That's the observation. And here's that 76% that's above. But we know we got to convert that to the below. So the area below would be its complement, 24%, right there. So my area below would be 0.24. So I need to figure out my z-score. Okay, so here I'm doing inverse norm, 0.24, 0, 1, just like that. So when I type that in, inverse norm, 0.24, 0, 1, it's going to give me a z-score of about negative 0.7063. I'm going to take it to 4 decimal spots just to be more precise. So now I know that my observation x equals the mean plus the z-score times the standard deviation. My observation is 38. My mean is 40.34. No, 35. 40.35. Okay, my z-score, I just solved for it, negative 0.7063, and the standard deviation is what I want. So it becomes an algebra problem from this point on. I have to take away the 40.35 from each side. So now I have, what do I have? I have negative 2.35 is equal to negative 0.7063 times the standard deviation. So now I just have to divide each side by the negative 0.7063. And then I'm going to crunch it. So negative 2.35 divided by negative 0.7063 will give me a standard deviation of about 3.3272. Just like that. Okay, next up. Heights of women aged 18 to 24 are approximately normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. What percent of women are shorter than 62 inches? Okay, so here I know it's normal. I know that my mean is 65 with a standard deviation of 2.5. Okay, we're looking for what percent of women are shorter than 62 inches. So again, if I picture this like that, here's my mean, right? I know that's 65. Here I'm looking at the x value of 62, and I want the percent that's going to be shorter. So I'm just building off of that kind of visualization. So here I can use, let's see, I can go through the z-score, that's fine, or I can use my raw data. So let me do it with my raw data. So negative infinity, I'm going to make my placeholder negative 9,999. That's typically what I do. Anywhere that's far below these numbers is a good placeholder for your infinity. Okay, so here I would do normal CDF. I'm going from negative 9,999 up to 62 with a mean of 65 and a standard deviation of 2.5. So let me type that in. So normal CDF, negative 9,999 up to 62. Mean is 65, standard deviation is 2.5. So here I'm going to get about 0.1151. Okay, and then here I just need to make that a percent. So I'd say, well, that's about 11.51%. Okay, the other way I could have done it is I could have found the z-score and done this whole process with the z-score. That would have been fine too. You just would have had the 0 and the 1 in these two spots, because if you're using a z-score, you're going to make sure that the mean is 0 and the standard deviation is 1 when you are typing into normal CDF. All right, next up. Heights of women aged 18 to 24, normally distributed, mean is 65, standard deviation 2.5. So we're seeing that same setup. How tall are the tallest 10% of women? So if I visualize this, here's my normal curve, here's that top 10% about. And we know that that marker is the same as the bottom 90. Okay, so here I can use my inverse norm. I don't have to go through the z-scores anymore because I know the mean and standard deviation and I know the proportion below. So I can say inverse norm, proportion below is 0.9, my mean is 65 and a standard deviation of 2.5. So if I plug that in, that's going to pump out the observation much quicker than if I did inverse norm 0.901. That would give me the z-score, and then I still have to use some algebra to get my x value, my observation value. So again, I'm all about the shortcuts at this point. So inverse norm 0.9, 65, 2.5. So that's going to give me an x value, my observation, of about 68.2039. And my units are inches. Okay, next up. The weights of ripe watermelons grown at Mr. Smith's farm are normally distributed with a standard deviation of 2.5 pounds. Find the mean weight of Mr. Smith's ripe watermelons if only 2% weigh less than 13 pounds. Okay, so we know it's a normal situation. We don't know the mean. We do know the standard deviation. So this is a finding the missing parameter type question. So if I picture it, here's my little normal curve. I don't know the mean, but I know it's about right there. We know that 2%, so here's that lowest 2%, weigh less than 13 pounds. So here's that lower 2%, just like that. So here, I don't know the mean. That's what I'm trying to solve for. I do know the standard deviation. So here, I'm going to have to figure out what is the z-score. I'm going to have to use the z-score and then go through x equals mean plus z times standard deviation. So over here, I can do inverse norm, 0.0201. So I can find out what is the z-score that goes with that proportion below. So here I'm going to do inverse norm 0.02,01, just like that. So that's going to give me a z-score of negative 2.0537. So z is about negative 2.0537. That's what's going to go in right there. So x, 13 pounds, equals the mean, don't know it, leaving mean right there. Z-score, negative 2.0537, standard deviation, 2.5. Okay, so now it's just an algebra problem. So 13 equals the mean, it's going to be minus, I just have to crunch. So here I have 2.0537 times 2.5. Okay, so I get 5.1343. So minus 5.1343. And then that's what I'm adding to the other side of my equation. So my mean will be, well, it's about 18.1343. And my units are pounds. All right, next up. While only 15% of babies have learned to walk by the age of 11 months, 80% are walking by 14 months. If the age at which babies develop the ability to walk can be described by a normal model, find the mean and standard deviation. So often I give you this little hint, find the standard deviation first. Okay, and I'm not giving you a lot of room, so I'm going to try to put these two pieces of information on the same normal curve. So we're told that 15% learn to walk by 11 months. So right here we'll say would be that 15%. So we know that this would be the area of 0.15. That is an x value of 11 months. Okay, I need to find the z-score. I'll find that in a moment. And then we know that at 80%, so right about here we'll say, at 80% we have them walking at 14 months. So area proportion below would be 0.8 and x is 14. So to find the z-scores, I'm going to use inverse norm. So I have inverse norm. Here I have 0.1501. And here I have inverse norm 0.801. Okay, so let's get those z-scores. So inverse norm 0.1501. It's going to give me a z-score of about negative 1.0364. Okay, over here, 0.8, 1, and I get a z-score of about 0.8416. Okay, so now I need to get to my standard deviation. So standard deviation, I need to know what's the difference between my observations. Okay, absolute value, I can take it in either order. So if I take 11 minus 14, right, that would give me something negative, which I then have to force positive or go the other way. Doesn't matter. I'm going to say 14 minus 11. I know it's going to end up being 3. They're 3 units apart. Okay, divided by how many standard deviations are they apart? So I'm looking at the difference between their z-scores. So I'm going to take 0.8416, take away a negative 1.0364, which I know turns into a plus right there. So if I take 0.8416, add 1.0364, they are 1.878 standard deviations apart. So 3 divided by 1.878 will get me a standard deviation of about 1.5974. So I know my standard deviation, my units would be in months. Okay, so then I have to get to my mean. So I would go x equals the mean plus the z-score times the standard deviation. I'm going to pick one of these points. It doesn't matter which one. I usually pick the first one. So here I know that the x value here was 11 months. I don't know the mean. I do know the z-score here, negative 1.0364, and my standard deviation, I just solved for it, 1.5974. Okay, so I need to crunch that. So I have negative 1.0364 times 1.5974. So 11 equals the mean minus 1.6555. And then I'm adding that to the other side. And I'm going to get a mean of about 12.6555, and my units are months. All right, so I'm trying to hit all of the good stuff today, everything that I feel is worthy of a little extra practice. All right, flip it, second page. All right, for 11. A professor asked her students whether or not they were registered to vote. In a sample of 70 of her students, 35 said that they were registered to vote. Find a 95% confidence interval. We underline that, that is crucial. For the true proportion of the professor's students who are registered to vote. So first I have to figure out what's the critical value. So what's the critical value for 95% confidence? So what I'm picturing, right here's that middle 95% of my data right here. I have the 5% in these two tail regions. I split it two ways. So I have 2.5 here and 2.5 here. So I need to know what would be those z-scores, and ultimately I'm just taking the positive because I'm thinking of it as a magnitude, as a distance from the mean. So here I know that I'm going to do inverse norm 0.02501, just like that. So it's going to give me a z-score here of about negative 1.96. I know this one would be positive 1.96, but when I think of a critical value, I'm always thinking in terms of the positive. And I've always had you round the critical values to 2 decimal spots. So my critical value is 1.96. Okay, I know that my sample size is 70. My statistic, the 35 out of 70 is just a half, and its complement would also be a half right there. So next I need to figure out what's my confidence interval. So confidence interval. And loosely, we think of it as our statistic plus or minus the margin of error. So if I'm being more technical, statistic plus or minus the critical value times the standard error. So p hat times q hat over n, and then square root just like that. Okay, so if I plug in those values, my statistic is a half plus or minus my critical value, 1.96, big square root, 1/2 times 1/2 divided by 70. Okay, so when I type that into my calculator, I'm going to get 0.5 plus or minus 0.1171. So here, that's my margin of error. So 1/2 right here, right? 0.5 plus or minus 0.1171. You can leave it like that, or you can attach it. So if I take 0.5 and I subtract 0.1171, I would get 0.3829. And if I add it, I would have 0.6171. So I could build that window, that's fine. Or I could write it as a percent. I got lots of options for you here. So let me just write it that last way, and then I'll move on to the next problem. So all 3 of these are fine. All of those are an acceptable answer for me. You pick your preference. All right, problem 12. A credit card company is about to send out a mailing to test the market for a new credit card. From that sample, they want to estimate the true proportion of people who will sign up for the card nationwide. The company wants to predict the proportion of customers with a margin of error of no more than 1% at the 99% confidence level. How many people should they mail? Use a p-hat value statistic of 0.5. Okay, so they want a margin of error of no more than 1%. And they're saying 99% confidence level. So we're saying the margin of error has to be then less than or equal to 0.01. So I need to figure out what is the critical value that goes with, sorry, let me start that over. I'm writing something wrong. That goes with 99%. So find the critical value. Okay, so if I picture, here's my normal curve, here's 99%, right? There's most of my data, 99%. So then I know that I'm taking that 1%, splitting it 2 ways. So this would be 0.5%, and 0.5%. So I'm going to have to use inverse norm, 0.00501, to get my z-score that goes with it. So I'm going to get negative 2.58. So my critical value will be 2.58, just like that. There we go. So now, I'm just going to write really small here because I didn't leave you a lot of room. I want to figure this out. So I know then that my margin of error has to be less than or equal to 0.01. So I know then that my critical value, 2.58, times the standard error, so 0.5 times 0.5 over n, and all underneath that same square root, has to be less than or equal to 0.01. Okay, now my fancy colors. So now it's an algebra problem. I want to get the n by itself. So I'm going to start by dividing each side by 2.58. So right here and here, those parts will cancel away. So now I'm going to have 0.5 times 0.5 over n, all underneath the same square root, is less than or equal to 0.01 over 2.58. Okay, so now to unlock that square root, I have to square each side. So I'm going to raise each side to the second power, like that. So now I have 0.5 times 0.5 over n is less than or equal to 0.01 over 2.58. That's a quantity squared. So notice that I haven't touched my calculator yet, right? I'm not touching it until the very end. Okay, I want to clear my fraction, so I'm going to multiply each side by n. So now I have 0.5 times 0.5 is less than or equal to 0.01 over 2.58 squared times n. So the last thing to do then is divide each side by 0.01 over 2.58 squared. Because over here, that part cancels away. So let me type this in. So parentheses, 0.5 times 0.5. There's my numerator. Divided by, I'm going to open two sets of parentheses. So there we go. There's my 2. So I'm going to have 0.01 divided by 2.58, closing parentheses, squaring it, and then closing my outer set, just like that. So when I hit enter here, oh, how lovely. I got an integer value. I love it. So n has to be greater than or equal to 16,664. So let me write that where I have some room. N has to be greater than or equal to 16,641. Okay, so how many people should they mail? Right, they should mail 16,641 individuals. Right, that would create a margin of error that is no more than 1%. Okay, so then my answer would be, what is the, how many people? I'll just say that n is equal to then that integer value. Okay, next up, let's practice a hypothesis test. So a National Center for Education Statistics monitors many aspects of elementary and secondary education nationwide. Their 2010 numbers are used as a baseline to assess changes. In 2010, 34% of students had not been absent from school even once during the previous year. In the 2016 survey, responses from 8,302 random students showed that this figure had slipped to 33%. Do these figures give evidence that student attendance is getting worse? Carry out a test at the alpha level of 0.05. That's your significance level. You may assume that the 4 assumptions have been met and the distribution is approximately normal. So I'm not making you labor through all of the checkpoints this time with the 4 assumptions. So we know that our sample size, n, is 8,302. Okay, our p-value, I don't want to say p-value, our parameter, let me say it like that, our parameter is 0.34. And then its complement would be 0.66. Okay, so we're told again, right, there's our 34% who have not been absent from school even once the previous year. This is what we're getting from our statistic, from our sample, and we are building our problem based on what we have heard as our true parameter. So our null hypothesis, business as usual, right, maintaining the status quo, is that that parameter is 0.34. Okay, and we're saying, well, we think that that may have slipped. So in the alternative, we think that it's actually less than 0.34. Okay, so when I calculate my p equals 0.34, again, that's my parameter, that's the mean that I'm building my distribution around. Okay, my statistic is lower. My statistic is 0.33. Okay, what is the standard deviation? So big square root, here is p times Q over N. Okay, and then when I plug that in, I'm going to get 0.0052. That's my standard deviation. So now what is it that I'm solving for? Let me draw my normal curve. Right, here's my mean, 0.34. My statistic, 0.33. And I'm looking at what is the p-value? What's the probability that we fall in this region? So I'm going to have to go to my normal CDF. Here's negative infinity, my placeholder, negative 9,999. So I'm going to say normal CDF from negative 9,999 to 0.33. Okay, my mean is 0.34, and my standard deviation, 0.0052. So again, this is my lower cutoff, my upper cutoff, right? So negative infinity to my statistic. Here's my mean and standard deviation. So I'm going to get a p-value. Here's where it's appropriate to say p-value for probability value. So my probability for this scenario playing out would be 0.0272. So again, what does that mean? Right? If the true proportion of students is 34%, we'd expect to see this result, right, the 33% or less, in only 2.72% of samples. So let me write that out for you just to have it in your notes. So if that true parameter, the true proportion of students is 34%, we would expect to see this result, which was 33% or less, in about 2.72% of samples. So is that unusual or not? So we're looking at that alpha level right here, that 0.05 or 5%. So we know that if we come in with something that is under that threshold, then we're going to reject the null hypothesis. So we're going to reject if our p-value is below 0.05. And we absolutely are. We're saying, man, that's pretty unusual for this scenario to play out. So if I summarize it, we're going to say, with this p-value, so with a p-value, with a probability value of 0.0072, or no, I wrote that wrong. Let me fix it. 0.0272, we reject the null hypothesis. Okay, we're saying this result is so unusual if we assume that our true parameter is really 0.34 or 34%. So instead, we rule in favor of the alternative. We believe there is sufficient evidence to support the claim that student attendance is getting worse. Okay. All right, two more. I'm going to try to be quick. All right, so here a pregnancy test is designed so that it will correctly detect pregnancy 99% of the time and correctly determine that a person is not pregnant 90% of the time. The hypotheses are Null, a person is not pregnant. Alternative, a person is pregnant. Explain what a type 1 error would be in this context and what the consequences may be. So a type 1 error is a false positive. Okay, so if I go back to what my constraints are here, null versus alternative, a false positive is saying, this is the truth, but this is what we are actually finding. So this is the truth, this is what we found. Okay, so our false positive would be, in reality, a person is not pregnant, but the test says that she is. So a person is not pregnant, but the test finds that she is. Okay, so what would be a consequence? Well, probably just disappointment. You know, if someone is planning or trying to get pregnant and they're finding out that that they're going to be in for a big wake-up call in the long run when they find out that they're actually not, right? So this will be disappointment when they find out that they're actually not pregnant. Okay, so the person is not pregnant, test finds out that she is. What happens? Disappointment in the long run when she finds out that she's really not pregnant, right? That false sense of joy that she's pregnant, but actually not. All right, and then lastly, 15, do more than 50% of U.S. adults get enough sleep? According to Gallup, 55% of U.S. adults said that they get enough sleep. The poll was based on a random sample of 1,003 U.S. adults. Interpret the p-value of 0.0001. So that's a probability, and that's a very, very tiny, tiny probability. So in this context, the null hypothesis would have been that p equals 0.5, and then the alternative that p is greater than 0.5. Okay, so saying that it looks like it has increased, right? That maybe it's more than 50% that get enough sleep. So the p-value of 0.0001 is so tiny. What is it saying? It's saying, well, if the true proportion, if that true parameter is 50%, I'm going to add my context. So true proportion of U.S. adults getting enough sleep is actually 50%, then we'd expect to see this results in only 0.01% of samples. Okay, so this result, which was 55% or more, in only 0.01% of our samples. Right, so highly unusual outcome. All right, that's all I have for today. I tried to be really thorough in trying to practice all of our big skills that we've been working on. I hope you guys are doing well. Have a great day.